Okay, so this will be the first of two videos on limits involving trig functions for Math 1560 Calc 1 at the University of Lethbridge. And we're going to cover some of the basic principles in this video, and then we're going to go on to tackle some of the sorts of limits that you might actually have to deal with in the course. But first we want to establish a few basic results. Now, in the last video, we left off with sort of a geometric argument involving triangles and a circle that left us with a couple of inequalities. I didn't put all the details in there, but if you want the rest of the details, the argument is also given in the textbook, so you can find it there. And we worked out this inequality here, this second inequality. That's one of the ones that we worked through. The one that I've given here first, if you go back and you look at what we had, you'll find that you can dig this thing out. We had that 1/2 sine x was less than or equal to 1/2 x, so multiply those by 2 and you've got it. Of course, we only really drew the picture in the first quadrant with x close to 0 but bigger than 0. It turns out that you can do the exact same thing in the fourth quadrant. You can consider negative values for x, and you can get similar inequalities, these ones that you see here, if you consider negative values of x that are close to 0. So we want to make use of these inequalities to establish a few basic results. Now, one of the things you'll see here is that the sine function is always squeezed in between 0 and x. At least when x is close to 0, sine x is between 0 and x. So keeping the squeeze theorem in mind, what do you think that's going to tell us? Well, that's going to give us, first of all, a basic result, right? The limit as x goes to 0 of sine x equals 0. This is straight up squeeze theorem, right? The value of sine x is always between 0 and x, and of course, as x goes to 0, x is going to 0, and so sine x must also go to 0. So we know that the sine function goes to 0 as x goes to 0, and of course sine of 0 is also equal to 0. So we know that the result is true when a equals 0. What about if a is not equal to 0? Well, it turns out there's a little trick we can do. We can do a little substitution. I introduce a new variable u, which is going to be the difference between x and a. And of course, if x is getting close to a, then the difference between x and a is getting close to 0. So instead of considering the limit as x goes to a of sine x, I can consider the limit as u goes to 0. Well, if I rearrange this equation, if I add a to both sides, x is equal to u plus a. So I can plug that in. And where do we go from here? Next step, we got to bring in a trig identity. So there is a trig identity that deals with when you have a sum inside the sine function, and it looks something like this. Sine u, sine a, plus cos u times cos a. And now you play around with the limit laws, and keep in mind that a is a constant. So sine of a, cos of a, those are constants. So we get sine of a times the limit as u goes to 0 of sine of u. Guys, I'm wrong, aren't I? Some of you were probably paying attention and you're shouting at me as you watch this video. I'm using the wrong identity. There we go. Okay. So that's correct now. Oops. There we go. Okay, so this is now cos a sine u, and then sine a, and then the limit as x approaches, u approaches 0 of cos u. Now, one of the things you could do here is, for this limit for the cosine function, you could rely on the fact that I could write cos u. Using the fact that sine squared plus cos squared equals 1, I can do some rearranging, and I can write cos u as 1 minus sine squared u. And so if I want to take the limit as u goes to 0 for cos u, I can use the fact, which you probably found in the textbook, you're allowed to bring the limit inside the square root. We know that sine squared u is going to go to 0. So as this part goes to 0, I'm just left with the square root of 1, which is just 1. So this term is going to go to 0. This term is going to go to 1. And what does that leave me with? It leaves me with sine of a, which is what we wanted. Okay, so now we know that we can deal with the sine function. If we have a limit involving just simply the sine function, we can do that by direct substitution. And a similar argument, basically relying on this, tells me that I can also deal with the cosine function via direct substitution. So that's good. We know how to deal with sine and cosine. Now, what about this limit here? This is a really important limit for, and really all the tricky limits involving trig functions boil down to knowing about this limit. So how do we know that this limit is true? Well, let's remember that we established early on that we had this result here. Cos x less than or equal to sine x over x less than or equal to 1. Okay, that was way back on the very first slide. That's the result that comes from this argument we gave in the last video, playing around with the areas of these triangles. Okay, well, we also know that the limit as x approaches 0 of cos x is cos 0, which is 1. And of course 1 is a constant function, so the limit as x approaches 0 of 1 is just 1. And so we have our result, right? The limit as x approaches 0 of sine x over x is 1. And why is it equal to 1? Well, because sine x over x is squeezed in between these other two functions. They're both going to 1, and so the squeeze theorem guarantees the result that we want. Alright, in the next video we're going to put this limit to use in some concrete examples.